All right, what do we mean when we say dissociation? First off, it applies to ionic compounds only. Ionic compounds are always a metal versus a non-metal. That means compounds like sodium and chlorine, potassium and iodine, and ammonium nitrate. Dissociation means unzipping them down the middle. And so what happens is they stop looking like the white solids that they look like and disappear completely into what we'll call aqueous ions. Let's take a look at what that looks like in solution. And we've got these three compounds that we'll be taking a look at. Remember, a positive and a negative, positive, negative, positive, negative. All right? And so here are these three ionic compounds. Here is our ammonium nitrate. Here is our potassium iodide. And here is our old buddy, sodium chloride. And behind them, we have a simple 1,000 milliliter beaker, and this is mounted on what's called a magnetic stir plate. And we're just going to watch what happens when we put these things in to a solution. So let's take a look. All right, so what we have is our magnetic stir bar in the bottom of our 1,000 milliliter beaker. We're going to add, we'll start with our ammonium nitrate. We'll add just an amount, and what we want to observe is this ammonium nitrate is a fairly solid white powder. It looks like, I'm trying to get a piece here. It looks like this, which I just dropped. And what we want to observe is what happens when we put this solid into our solution. Obviously, something interesting is going on, and eventually our white solid is slowly going to completely disappear. In fact, no evidence of our white solid remains. Let's try that with a couple other compounds. We'll try that with our buddy potassium iodide, and we're simply going to add a small amount. Again, what we want to observe is that this compound is a white solid, but what happens when we put it into solution? And let's observe. We see our white solid slowly disappearing, and eventually it will disappear completely. We'll turn our speed up a tad. And I may have put in a big chunk of it, but it's going. It's getting there. You can see it slowly disappearing. Turn this up all the way. And our white powder completely gone. Let's try one more. This is our old friend table salt, and this is a compound with which you should all be familiar. We all use a lot of this. Again, a white powder, but what happens when we put it into solution? And again, completely disappears. Some of us will say, well, it's dissolving. But with ionic compounds such as this, that's not the case. Let's go in the back of our molecular theory and take a look at what's going on. And so here are the three compounds that we just observed what happens in solution. And we saw them completely disappear from the white powdery solids that they are out of solution and completely disappear in solution. And what's going on? It's what we call dissociation. It works like this. Let's take this, our old buddy table salt, NaCl. And we know that it's an ionic compound that we could separate right down the middle into a positive and negative ion. Well, that's exactly what goes on when we put it in solution. So, what happens when we take this compound and put it in solution, what we call aqueous, that's this guy here, aqueous, it's going to stand for aqueous. It actually dissociates, it completely separates into a sodium ion that is positively charged and a chloride ion that is negatively charged. The concern that we have with a process like this is we want to be keeping track of the amounts. And so let's rewrite this equation. If we were to take sodium chloride and make it aqueous, we know it's going to dissociate into its positive and negative ions. Our concern is what happens to the amounts. And so if we were to dissolve 1 mole of sodium chloride in water, what happens? Well, we know that we've got 1 sodium atom and 1 chlorine atom. And so that means if we had 1 molecule of sodium chloride, when it dissociated, we would get 1 atom, now called an ion because it is positively charged, of sodium, and 1 atom, now an ion, of chloride because it is negatively charged. Well, what happens if we, instead of speak in terms of molecules, hang on, I had a massive technical snafu. Sorry about that, and we're back. Instead of speaking in terms of molecules, we spoke in terms of moles. Well, 1 mole of molecules is going to produce 1 mole of sodium atoms or ions and 1 mole of chloride ions. And this is where we start to perhaps get, things get a little twisted. What happens is this. If 1 mole of sodium chloride dissociates into 1 mole of sodium ions and 1 mole of chloride ions, that's 2 total moles. If we were to do this with, for example, say 3 moles of sodium chloride ions, or sodium chloride, excuse me, we would get 3 moles of sodium and 3 moles of chlorine for 6 total moles. And that's really the trick with dissociation. The only time it might get complicated is if we have a molecule that has more than 1 of a particular type of ion. Here is something called calcium chloride. It's right in the name, calcium chloride, and it dissociates right down the middle. That means that when we write the dissociation equation, it looks like this. Calcium 2+, and of course the other ion is the chlorine, but there's 2 of them right here. So we're going to put a 2 next to that chloride, because that means that if 1 mole of calcium chloride were to dissociate, we would get 1 mole of calcium because there's 1 atom per molecule. But we'd get 2 moles of chlorine for a total of 3 moles total. If we were to dissociate, like we did in the previous example, 3 moles of calcium chloride. When it dissociated, we'd get 3 moles of calcium because there's only 1 calcium per, and we'd get times 2, 6 moles of chloride ions, and that would be a total of 9 total moles. And that's the trick with dissociating, is paying attention to the formula so that you know how many of each type of atom are in each molecule. Remember that when we do this with molecules that involve polyatomic ions, like for example, say aluminum carbonate, which looks like this, that these parentheses mean this subscript applies to the entire molecule. So when aluminum carbonate dissociates, you get 2 aluminums and 3, remember this subscript 3 applies to the entire polyatomic ion, 3 carbonates. So when you did this, if you dissolved 1 mole of aluminum carbonate, you'd get 2 moles of aluminum because of that coefficient, and 3 moles of carbonate. We're not dissociating anything in the parentheses. We leave these alone. Okay? So how many total moles would we get? 5 moles total. And that's all you do. So take that for a spin, please.